talking about Taylor series. Before we had discussed the power series that came from the geometric series, 1 over 1 minus x, and different functions that we could get using that, which is a powerful technique because it's pretty easy. You just substitute and go. Now, the other question, though, is what if we have some kind of function that isn't of the form 1 over 1 minus x or anywhere near that form, say e to the x or sine x or tangent, whatever, something, right? So, what do we do then? So that's what Taylor was trying to look at, Taylor and Maclaurin, the other name that is in this section. And so the question becomes, let's say we have some arbitrary function f of x. We don't know what it is, but we do know that we can expand it as a power series around the point A. So by the way, for this demonstration, A is just going to be constant throughout, okay? So A is just some number. Often in practice, it's 0, which is always nice. But we're just going to leave it as A for this demonstration. So we're as general as possible. So let's say we know that we have this series and that it converges on some radius of convergence. Either, some radius of convergence greater than 0. So 1x minus A less than some big R. So the question then is, well, what are the C's? C1, C2, C5, Cn. Because if we know what Cn is, if we can figure out Cn, then we can figure out what the power series is. And as we were talking about in the introduction to this week, then we can use the power series as an approximation, however we want to use it as an approximation, however many terms we need. So, how do we figure it out? Well, one thing that we can realize is that if I put in, and we did this before, remember, if I put in A for x, this thing has to be true for all x in this radius of convergence, so it's certainly true at A, right? But if I put in x equals A, all these guys cancel out. They're all 0, except for this first term. So if I just evaluate f at A, all these are 0, and that gives me C naught. In other words, I know that C naught is f of A. So I'm going to write these over here. I do want to point out, so the point of doing this is, I can't really see that right now. Hold up. Okay, that helps. It makes it work. Oh, that helps a little bit. Okay, so you can see these a little bit better. The point is, for this kind of demonstration, this is a situation where we know what f of x is, but we're trying to figure out what the power series is. So if I put in, so I'm going to start with f of x being some function, sine, cosine, whatever, right? And I can figure out what all these things are. So in this way, but okay, so I figured out the first one. Well, that's just one term. I need all the Cn. But if you remember what we did before, we said once we're on our radius of convergence, we can take derivatives term by term. Okay, so if I just take the derivative here of this whole thing, what am I going to get? F prime of x, I'm going to get C1, and then the rest of this garbage, which I'm just going to write a few terms because I'm going to keep taking derivatives. I want to look at what they look like. Let's see if I can stick one in here. Dot, dot, dot. There would be a C5. Okay. So now what happens if I put in x equals A here? Again, all of this should be a minus, darn it. All these will all go out because they're all x minus A, so at x equals A, these are all 0. Only C1 is left if I put in A. So that's going to tell me that f prime of A is C1. Now I solve for the first two coefficients. I just can keep doing it until I can solve for as many as I want. Let's do the second one. Take the second derivative. Notice when I take the derivative all the way down, right? I take the derivative for all of them. So here I'm starting to see I'm getting more than just the one number, right? Because I take the derivative of 3 times 2, 4 times 3. The next one, okay, let me like put the next one in here because I have them up there. So this one would have been 5c5x minus a4 when I was doing the first derivative. So my second derivative, I'm going to have that term again. It's going to be 5 times 4 c5x minus a. Right, to the third, because I started here, this 5, I've taken derivatives twice, I'm down to 3. And it tells you here that the second derivative, once I plug in x equals a, is going to be 2c2, or c2 is going to be the second derivative of a over 2. Okay, so let's keep going. I'm going to keep my f of x up there so we can refer to him, but I'm going to keep taking derivatives. Third derivative, for the third derivative, I'm just going to take the second derivative and go through again, right? So this one's a constant 0. Then I'm going to have this, 3 times 2, c3. And then I'm going to have 4 times 3 times 2, c4x minus a. My fifth term is going to be 5 times 4 times 3, c5 x minus a squared. Okay. So then when I put in a, again, so for the third derivative, I'm going to be able to solve for c3. The same way for the second derivative, I'm going to be able to solve for c2, and back and back and back. Okay? So I've got the third derivative at a is 3 times 2 c3, or now here you're like, okay, why is she writing 3 times 2? Why isn't she writing 6? Right? But then I want to write 6 because 6 doesn't actually show me what's happening. Okay? That's why I wrote 4 times 3 times 2 and 5 times 4 times 3. I didn't write 12 and 20 because those are just sort of numbers that kind of mask what's really going on. And what's really going on is that this is actually a factorial. Okay? So this is 2. It's really like 2 times 1. 2 and 2 factorial are the same. I can put the 2 there. And here, I really want to write this as a 3 factorial. Because what's going to happen as I take my derivative each time is, and I'll do it on the next one, you'll see quite quickly, right? I've already got it here. This is 4 factorial. Right? Because I've got the 4 times 3 times 2. I don't need to write times 1. This one, I haven't taken all my derivatives yet, right? Because in the next step, when I take the fourth derivative, I'll still have an x minus a. Let me write it. Fourth derivative is going to be 4 times 3 times 2 times c4. Now this looks good, right? But I still have an x minus a, and then my sixth term would still not have my 2 yet, right? So you can see what's going to happen again. The same pattern is starting to emerge. We can see what it's going to be. The fourth derivative at a, this is 4 factorial times c4, because this term and all the rest are 0. There. Okay? So if I look at my C, and then C5 is going to be the fifth thing as well, right? The fifth derivative, and it's going to be the fifth derivative C5 is going to be the fifth derivative of A divided by 5 factorial. So this gives us the actual, we can see the pattern. The pattern is going to be that the nth Cn is going to be the nth derivative of the function evaluated at point A divided by n factorial. So that is the equation, right? The equation for Taylor's theorem. Okay? So what this is going to tell me, let me get rid of this stuff, is that if I take any old function I want, as long as it's smooth, right? Meaning I'm taking all these derivatives, that better make sense, right? I better be able to take the derivatives. Okay, so as long as it's differentiable, I can keep taking those derivatives and figuring out what these coefficients are, and then I can write down my series. Okay, so that's the thing. So let me take off this. So my idea being that now I can figure out what my series is. But there's a problem here. There's not really a problem. The problem is that you have to take a whole bunch of derivatives, evaluate them, and look for the pattern. So that's what we're going to be doing for the rest of this chapter. Okay? There is some subtle mathematics here, which is not entirely easy to show. All right? I already started with the assumption we can write down this function as this power series that converges. Okay, so that is my assumption. In order to show this, and this is what Taylor did, you have to do it the other way, right? You have to make sure that you're going to get something here, given some function, using these particular coefficients that we figured out they have to have this form, which is good that we did that, so now we know. But we still have to show that this is going to be then a convergent power series that, all right, that will converge to that. So that's the work of proving Taylor's theorem, which I will link something about it, but it's not something that we're really going to do in this class. Your book writes about it too. Basically, you write down the thing as a finite polynomial plus some remainder term, and you show that the remainder term goes to 0 as n goes to infinity. So that's how that's proved. If you don't care about it, you don't have to worry about it, but I will link it for you guys if you're interested. Okay. So let me do at least the most simple basic example that we can figure out pretty quickly. And then I'm going to continue to go on in further videos to do some more examples. And also, I hope you will take a look at the video where we actually graph these things, okay? Because that's kind of nice. It gives you some pictures for what's really going on. All right, so we're going to use the function. The very first example is going to be f of x, because this is a super easy example, like e to the x. And we're going to do it around the point a equals 0, by the way. So if a is equal to 0, it's still a Taylor series, but it's sort of the special kind, and we call that the Maclaurin series. So Maclaurin series is just Taylor series with a equals 0. Yeah. So what are we going to do? We're going to evaluate this thing. Right? So C0 is f of 0 in this case, right? So this is e of 0, so this is 1. And now I have to take successive derivatives, but that's why this is such a nice, easy example, because we know what the successive derivatives are here, right? I just keep taking derivatives, and it's e to the x So all of the derivatives are e to the x, right? That means that when I start putting things in here, right, and each of these is going to be e to the 0, so if I put in C1, right, which is going to be f prime of 0, that's just e to the 0, which is 1. C2 is going to be second derivative at 0 over 2 factorial, right, which is e to the 0 over 2 factorial. So I have this, and maybe you can realize this is 1 over 1 factorial if you want, so it's just 1. And so you see what's going to happen. This is so nice. So I have 1 over 3 factorial, and my nth derivative, Cn, is going to be my nth derivative at 0 divided by n factorial. So I just have 1 over n factorial. So this is really what I need. I don't have to do anything fancy, and then I write this down, right? I'm going to write down that e to the x is the sum from n equals 0 to infinity of Cn xn, where Cn is given by that. So is x to the n over n factorial. Okay? So this is actually a representation of the function e to the x. It's a super important one. You guys will use this a lot in your lives. Maybe not, depending on what you do. But if you continue studying mathematics, you'll use this a lot in your lives. And this gives us a representation. It gives us an ability to compute. In fact, how does your calculator compute e to the 5? It just writes down this series, and it computes it to a certain level of, let's see, what do you have for e to the x? So I've got 1 plus x squared over 2 factorial. So if I just write it out, if your calculator wants to compute, okay, e to the 17.2, it will simply compute this with x equals 17.2 or whatever it is. Okay, and it'll compute it up to, I'm not entirely sure how many you need to do. This is something that you use Taylor's theorem for, which we're kind of skipping this class. We're like close to the end. But so we don't have to worry about that right now. But you can just compute this up with some finite sum, and you'll be pretty close to the exact value. Okay. Now the other thing that I want to say before the end of this video is up here it says something about the radius of convergence, but this process finding Taylor's theorem, Taylor's series expansion, which is what this is, does not tell you anything about the radius of convergence. So what you have to do is you have to first do this and then go back to what we did in the last chapter to compute the radius of convergence, right? So you would then go ahead and use the ratio test on this to show the radius of convergence. Okay. Luckily, for this particular series, I think we already did this series. I think it was one of my first examples. And we showed that the ratio test shows that the radius of convergence of this is infinity. This converges for any x. Okay? Not all of them will be like that. Obviously, our previous example with the 1 over 1 minus x, which, by the way, you can also work out this way. If you want, you'll get the same thing. That one obviously has a radius of convergence of 1. They're going to change. It's going to be dependent on whatever it is. But this guy has a radius of convergence the whole real line. And we already showed that.